Please look at this figure. The field lines are parallel and equidistant lines, suggesting the field is uniform. The lines are going through the surface of this area perpendicular to the field. We know the number of lines per unit area perpendicular to the lines is proportional to the magnitude of the electric field. Hence, the total number of lines penetrating the surface is proportional to the product of the magnitude of the electric field, E, and surface area, A. The product of E and A is called electric flux. We use the symbol phi E to represent the electric flux. This equation is valid only for a very special case where the electric field is uniform and the flat surface is perpendicular to the field lines. Please look at this figure. If the surface is not perpendicular to the field, how to define the electric flux? Let's consider the uniform electric field firstly. We can see the normal to the surface of the area A is at an angle theta to the field. According to the definition of the electric flux, the number of lines penetrating A equals the number of lines that cross the area A vertical. A vertical is a projection of the area A onto a plane oriented perpendicular to the field. The area of A vertical is equal to the area of A multiplied by cosine theta. So the flux through A is expressed by this one, phi E equals EA cosine theta. From this expression, we can find that the flux is maximum when the surface is oriented perpendicular to the field, where the normal to the surface is parallel to the field and theta equals 0 in this case. The electric flux is 0 when the surface is parallel to the field, where the normal to the surface is perpendicular to the field and theta equals 90 degrees. But if the field varies over the surface, in other words, the field is non-uniform, how to calculate the electric flux in this case? In more general situations, the electric field may vary over the surface. We can divide the surface into many small elements. Each element has the area of delta AI. We define a vector delta AI in such a way the magnitude of which represents the area of the ith element of the large surface, and the direction is defined to be perpendicular to the surface element as shown in this figure. The electric field EI at the location of this element makes an angle theta I with a vector delta AI. The electric flux through this element can be calculated using the formula we got above, where we employed the definition of the scalar product of two vectors. Summing the contributions of all elements gives the total flux through the surface approximately. However, this is just an approximation. How to get the accurate calculation for the electric flux through any shaped surface in a non-uniform field? If the area of each element approaches 0, the number of elements approaches infinity, and the sum is replaced by an integral. Therefore, the general definition of the electric flux is the integral of the electric field over the entire surface. Next, let me introduce a closed surface in the electric field. We wish to find the electric flux through this closed surface as shown in the figure. So what is a closed surface? A closed surface is defined as a surface that divides space into an inside and an outside region so that we cannot move from one region to the other without crossing the surface. By convention, the area vectors are normal to the surface and point outward from the surface in this case. Please look at this figure. Obviously, the vectors delta AI point in different directions for the various surface elements, but for each element, they are normal to the surface and point outward. We can notice that the sign of the electric flux here depends on the angle between the normal to the surface and the electric field. Please look at this figure. At the location 1, the field lines are crossing the surface from the inside to the outside. In this case, theta is smaller than 19 degrees, and the flux is positive. At the location 2, the field lines graze the surface, where theta equals 19 degrees exactly, and the flux is 0. At the location 3, the field lines are crossing the surface from the outside to the inside, and the flux is negative. Hence, the flux is scalar quantity but is sign-sensitive. Based on the discussion above, in order to determine the flux through any closed surface, we must know the net number of lines leaving the surface because the net flux through the closed surface is proportional to the net number of lines leaving the surface. Then, what does the net number mean? The net number means the number of lines leaving the surface minus the number of lines entering the surface. If more lines are leaving than the entering, the net flux is positive. On the other hand, if more lines are entering than leaving, the net flux is negative. The net flux can be calculated by the integral of the electric field over the entire closed surface as expressed by this equation. Now, let me give you an example here. Consider a uniform electric field E directed along the x-axis in empty space. A cube with a length L placed in the field, oriented as shown in this figure. Please find the net electric flux through the surfaces of the cube. This is a closed surface which consists of 6 faces. We could obtain the total flux by summing the flux through each face individually. It's noted that the electric field lines pass through the phase 1 and the phase 2 perpendicularly and are parallel to 4 other faces of the cube. Therefore, the net flux through these 4 faces is 0. The flux of the phase 1 and the phase 2 can be calculated by using these 2 equations. Then the net flux is obtained by adding the flux over all 6 faces and equals 0. Now, I have a question here. We found that the net flux through this cube is 0. Is this coincidence due to the shape or orientation of the cube? In other words, if we have a closed surface with an arbitrary shape, how about the flux? Obviously, if there's no charge inside the closed surface, all field lines that get into the surface have to come out. Hence, the electric flux through a closed surface that does not contain the charges must be 0. Then, what if the closed surface contains charges? Let's explore it in details next lecture.